is just going to give us some more tools for deciding if things are linear or not. And the main thing that we're talking about today is what's called the coefficient of determination. That's the r squared. Remember when we run the regressions, we see that ax plus by gives us ab, r, and r squared on that same screen. So now we're actually talking about what that r squared is. So that's our coefficient of determination. What it's giving us is the proportion of the variation in the response that's explained by the regression line. It's telling us what percentage of the variability is the regression line giving us. It will always be between between 0 and 1 because r fell between -1 and 1. If it's 0, that means it's not explaining anything. If it's a perfect 1, that means it's explaining 100% of the variation. There's different types of error that we can look at. This picture, you don't necessarily have to write this down. I really just want you to kind of have some idea if you ever hear these words. This isn't something I'm really going to test. But we're talking about deviation, like how the points are different than we predict them to be on the line. So if I'm talking about the total deviation, that's saying for a particular point, how different is that point from the average? So y bar is the average y value. And we know that not every point is going to be equal to the average, right? If I give a test and I tell you the average was an 85%, does that mean every one of you got an 85%? No. So deviation is talking about how far you are from that average point. So if I had an ordered pair x, y, my deviation is how far is that y from the actual average. And we have two kinds of deviation. We have explained and unexplained. Explained is this distance between the average and the line. Because the line, when you write the equation of the line, it takes into account the average. We use that y bar when we write that equation. So that's explained by the line. That's just the variability in the numbers, but the line takes that part into account. Unexplained variability is the difference between the line and your point. So really, what I just want you to get from this, when we're talking about the deviation or the variability here, there's explained and unexplained. Explained we expect because we know not every point is average. Unexplained is why didn't my point fall on my line of best fit? Okay, there are lots of reasons for that. We know that if we take real life data and we try to make a line of best fit, it's impossible for every point to fall on that line. So that's our unexplained deviation. There are other factors that could have came into play there that would have that impact. Okay. Again, I'm not really going to test this. I just kind of wanted you to hear those terms in case you ever did see them anywhere. Any questions so far? So what I want to do first is let's actually find the r squared, the coefficient of determination here. So to do that, we're going to use our calculators. So go ahead and pull that out. Okay, so we're going to go to Stat, Edit, and let's put this in our L1 and L2. Then we are going to run the linear regression, just like we did when we did lines of best fit or finding R. So you go to Stat, calculate number 4. We enter through all of this. Okay, it tells me my line of best fit. If I ask for that equation, it gives you your A and your B. The R we've seen before. If we had R, we can get R squared just by squaring it, but this tells us directly. R squared is 0.9882. Yes, ma'am.
Whenever I do all that, mine doesn't show up like the R or anything.
You need to turn your diagnostics back on. So go to second 0. And that should take you into your catalog, and you scroll all the way down to diagnostic on. I might ask you what this means. Actually, I probably will, especially on the test. Probably ask what that tells us. So this means 98.82% of the variation in Y, which for us, our Y was the weight, is explained by the regression line. So that means for this particular example, there's only 1.2% of the variability that's unexplained. So this is an excellent line. It's explaining almost 99% of the variability. So the higher your R value, the better it is. A low R value or R squared value tells us that your line doesn't explain very much, so we have a lot of other factors going on. So it's not as good of a fit. You guys have that down? The next slide, I just put some pictures to kind of illustrate what we just talked about there. So this is just showing us 3 different sets of data. The first one, you notice it was almost perfectly on the regression line. Almost every point is on that line. That one, my R value is 99.99%. So almost 100%. This one, you notice they're a little more spread out. That one's only explaining 94.7%. The last one, you can see that's not a very good line at all. That one is only a 9.4%. So the better fit your line is, the higher your R squared should be. Any questions about that? The second piece that we're going to talk about are residuals. So residuals are just a way of looking at this variability. We are not doing anything by hand when we say residuals. Our calculator is going to do it all for us. So we are going to look at what are called residual plots, which is just a scatter diagram with these residuals, which measure our variability. It's kind of maybe not what you might expect when you're looking at a residual plot. And if it were me, I might draw just a rough sketch of each of these. This first one is actually the case where a linear model is a good fit. When you draw the residuals, you don't want any kind of pattern. Basically, you want 0 in the middle and kind of an even spread, points above and below 0. Okay? We're looking kind of just like a horizontal section of points. If you have a pattern in your residuals, if I'm looking at this one, you know, it's kind of a little quadratic looking. that's bad. That means it's not linear. So when we plot the residuals, if there is no pattern, that means it's linear. If you do see a pattern, that tells us that there's something wrong. I say not linear, but it's more that this linear model isn't a very good one for that scenario. The residuals are plotting how far it is from the average. So if it's a good line, you should have about the same amount above and below average. When you see these patterns, it's telling us that, well, early on, my line, I had a lot of points above average, and then they were all below, and then they went back to being above. So that was bad. It wasn't consistent. So let's look at one. So using that same set of data that we were looking at, I want to decide if this is linear. So looking at the R and the R squared, it seems pretty good, didn't it? So what we're going to look at now are the residual plots. To do that, on your calculator, you have to have your data entered, which we already do. You also do have to run the linear regression. That was one of the problems we figured out last hour. If you don't run the regression first, it doesn't work. So we already have, for this set of data, we don't have to do it again. I want you to go to second stat plot. And let's go into plot number 1. Okay, we want a scatter plot. But this time, I want it to plot my residuals, not the actual y value. So if you go down to your y list, I need you to hit second stat. This gives us our options, and we want the number 7, the residual. Now we go to zoom number 9, and here's my residual plot. Hold on, I have some other equations entered. I need to delete those out. Okay. So if I'm looking at my residual plot, is my linear model the best? Is there a pattern? Yes, and if there's a pattern, what did that tell us? Not linear. That's the reason we look at residuals, because sometimes the R values are misleading. When we looked at our R, it told us it was pretty strong linear relationship. Our residual here is telling us it's not linear. What's actually going on here is it's saying there's a problem with our line. It's saying your line of best fit, early on your points were above that, so it was an overestimate at the beginning. Then all my points fell below, so then it turned into an underestimate, and then it went back to being an overestimate. If it's a great line, it'll be evenly dispersed above and below 0 all the way through. So looking at this, we would say not linear. I'm taking a test, you could just give me a rough sketch. So what that means is it was an overestimate at the beginning and end. Underestimate in the middle. So it was not the best fit. Okay. Not so much telling us that we can't have a line of best fit, but that there's some problems with that line if we were looking at it. There is a second issue that the residuals can show us, and that's what's called constant error variance. So ideally, if the data is great, it's evenly spread around 0, and it's just like a flat section. You have points, just horizontal section above and below 0. If I look at this one, if I'm looking, this original graph here shows my original scatter plot and line of best fit, and it doesn't look like a bad line. Look at my residual plots. First of all, is there a pattern there? No, so we didn't break that rule, but look what happens. As time goes on, this thing is spreading out. What that's telling us is that at the beginning, my line was a really good fit. But as time goes on, my points are getting further and further away from the line of best fit. So it's a good model early on, but later on, it's less accurate. If we look at our actual line of best fit, you can see when we start getting down here, don't you have more points further away from your line? Yes, so it's becoming less accurate as time goes on. So that's constant error variance. So the two things that we're looking for when we look at our residuals, do we have a pattern? And do we have an error or a constant error variance issue? Or is it like cone shaped? Either direction. It could be that early on the points were really spread out and later on they became more consistent. Residuals are also good for telling us if we have outliers. We've talked about outliers before in several different instances. So I have pictures just talking about some of the instances where we've looked at those outliers. This is just your basic scatter plot, and so you can see that point kind of looks like an outlier from the scatter plot. If you plot your residuals, the outliers become even more obvious because you've got all your points spread right here around 0, and then I have one point out of that bar, out by itself. We have also talked about, if I give you a box plot, we know what an outlier looks like there. It's outside the whiskers. So we can look at the outliers on a residual as well. So let's look at another example. This is the drilling example that we've used a few times now. I want to draw the residual plot and decide if the regression line is a good fit or not. So you have to go to your calculator and first of all enter everything in L1 and L2. if you try to just do the residual plot right now, you will get an error message. We have to first run the regression before it will work. So we need to go to Stat, calculate number 4. So now it has the equation for the regression line. It's got the R squared. Now we need to find if the linear model is appropriate, so we're going to use the residuals. So if we go to our stat plot, we already have it turned on to residuals. Just an FYI, if you don't want residuals, then you'll have to go back in and change your Y list to L2 again. Now we can go to zoom number 9, and here is my residual plot. Okay, it's not perfect. You have questions? Okay. On the homework, just very rough. If I ask you to do a residual plot, do it on your calculator, and I'm not even expecting the same number of points, just put some dots to kind of show me the general shape. So this one, I mean, it isn't great. We see, you know, we do have some points right there, and it kind of spreads out a little bit, but it's not a clear pattern. There's not a ton of points here to really make that obvious. So this one is fairly good. There's no clear pattern. We don't have a parabola or anything like that. As far as the cone shaped, you know, it kind of looks for a second like maybe it's going to spread out, but then we had points back closer to 0 again, so it's not really cone shaped. Do we have any outliers here? No. So this one is a pretty good model. Okay, and we checked all of those things. There were no outliers, no pattern. So that one's okay. The last thing I want to mention is when we look at outliers, some outliers make a bigger difference than others. We can talk about influential and not influential outliers. If I just look at this picture, I have 3 outliers. Some of those will make a big difference, and some will not. For instance, you know, this first one is definitely an outlier. It's a lot higher than the other points. It doesn't follow that trend. Same thing with this third one out here, far below. This second outlier, it's farther away from my points, but does it follow the general pattern of my points? Yeah, so if we were actually doing our line of best fit, will that outlier change the equation of my line much? No, it's going to have very little impact. Now, will 1 and 3 have a big impact on my line? Yes. So 1 and 3 would be considered more influential than the second one. The third is probably the most influential. If you're measuring how far it is from the line, it's going to take that line and drop it down. So it's probably the worst. If we're trying to decide if a point is influential or not, what we can do is look at the equations of the regression lines with and without that point. So that's going to be our final example for today. We're going to add another point to our drilling example and see if we have an influential point or not. I want to take an additional point. First, let's write down the regression line before we add that point in. So I know we already ran it once, but I didn't write it down. it wants us to say at a depth of 300. So we're going to go back to our stat, edit, and we're just going down to the bottom. We're going to add in this new point. So when my x is 300, my y was 12.49. Now we run the regression again. So stat, calculate, linear regression. And now my equation is 0.0212x plus 4.443. Alright, can you tell just by looking at that if that's a huge difference or not? Maybe. Sometimes it's really obvious. Here, you know, there is a difference. I don't necessarily know how significant it is. Let's graph it to see. If you go to your y equals, we can enter these as our y1 and y2. Then if we look at our graph, oh, hold on, we need to change something. Our scatter plot was set to graph residuals, right? I want to graph the actual points. So go into your stat plot. For your y list, let's change that back to L2. So you can either just hit second 2, that does it, or if you go into second stat, then you can select the L2. Let's go zoom number 9. So there's my original scatter plot. That blue line is my original line. We can see this point was definitely an outlier. The red line is the new one. So did that outlier change my line quite a bit? Yes, it did. If the lines are very close to one another, then we say it's not influential. But here, we can see it took my line and it did make a big change, so that one is an influential one. So this section relies heavily on the calculator. It's really all about looking at the graphs and the scatter plots on your calculator. Any questions for me? So that is the end of this section. The homework, this will be due on Tuesday. So Monday you will have class time to work on this, and I will also give you your study guide.